Welcome everyone to our video on the Bohr model of the atom. Now this video is going to be a pretty important video for us. It will lay the foundation for the modern atomic models that we will end up with. It will also form the foundation for a lot of our unit on chemical bonding, as well as our analysis of periodic trends. So you really want to focus on thinking deeply about the concepts introduced in this video and making sure you have a firm grasp of the different aspects of Bohr's model. One suggestion here is that for this video, you may want to just simply watch the whole thing through first without bothering trying to fill in the worksheet and just listen. And then go back, watch it again, pausing as we go to fill in the blanks on your worksheet. But you might find that an effective way to really solidify the information. In this video, we are going to start off by introducing some of the limitations of the nuclear model to set us up for why there was a need for a new model of the atom. Next, we're going to list the key features of Bohr's model of the atom, and then we are going to connect the experimental evidence that we have to the features of the model. So just as a review, here is the nuclear model of the atom, Rutherford's model, where Rutherford stated that the positive charges of the atom are confined to a dense nucleus, and that's where most of the mass is. And then most of the atom is empty space, and that's where you find the electrons moving randomly about. So our first limitation is a big one. It has to do with the attraction between the electron and the nucleus. According to classical physics, if you have two things that are oppositely charged, they're going to be attracted to each other. And if one of them has some momentum, so it's moving in some direction, it's got mass, it should spiral into the nucleus, as you can see in this diagram here. So what is it that's causing those electrons to be stable and preventing them from collapsing into the nucleus due to their attraction? The second limitation is the opposite. What about those electrons that are far away from the nucleus? Why are they stable as well? Why aren't they constantly being lost because they sit so far away from the attractive force of the nucleus? So these two limitations, they're really examples of the same larger limitation, is what's causing the stability of the electrons. Our third limitation has to do with the nucleus. So as we've learned, the nucleus is filled with positive charges, and Moseley showed that those positive charges are unique subatomic particles, protons. So what's holding all of those positive charges together in the nucleus? And they're crammed in there in a small, dense space. So what's the force that's overcoming the immense force of repulsion from all of those protons? So this third limitation, we are not going to address with Bohr's model. We'll just suffice to say that it was addressed with nuclear physics and understanding the forces within the atom. We're going to deal with the electrons today. So let's start off with Bohr's model of the atom and just his features about what he said about the atom. Once again, we're focused here not on the nucleus, that kind of remains the same, positively charged nucleus. We're focused on the electrons. So first of all, Bohr said that the electrons aren't just randomly moving about, but they are confined to distinct energy levels. And these energy levels are at fixed distances from the nucleus itself. There can be multiple electrons at a single energy level, and all of those electrons are equivalent in energy. One of his key ideas here is the idea that electrons do not exist between these energy levels. they are confined to these energy levels and they're never found in between. As we move further and further from the nucleus, these levels increase in energy. So an electron at an energy level close to the nucleus is lower in energy than an electron that is further away from the nucleus. Next point here is what's referred to as the Aufbau principle, which is building up. And it's the idea that electrons will always occupy the lowest possible energy level. So if there's room on a lower energy level, the electrons will fill that gap before occupying a higher energy level. And Bohr's model also has a capacity for each energy level, and it's given by a formula 2n squared, where n refers to the energy level, and the energy level is just an integer starting at 1, 1, 2, 3, 4, and so on. So you plug in the energy level in for n, and that tells you how many electrons can fit on that energy level. N equals 1. 1 squared times 2, 2. So there's 2 electrons on the first energy level. N equals 2. 2 squared is 4. Times 2 is 8. On the second energy level, 8 electrons. And going up from there. So as you can see by that formula, as we move further away from the nucleus, the levels increase in energy, and they also increase in capacity. Our main focus for looking at the evidence for Bohr's model is the line spectrum of the elements. So Bohr did not invent the line spectrum or discover it. It was a known fact that when you heat a pure element and you look at the light that's released and you put that light through a prism or some form, an advanced form of a prism, we get a distinct number of lines. So we will see the line spectrum in class as a demonstration. And we call this the line spectrum. It's very similar to the effect that we see when you see a rainbow. So when you see a rainbow, that's a continuous spectrum. We see all of the visible colors of the spectrum. A line spectrum, we only see distinct lines and there's lots of gaps in between those lines. It's also known that each element produces a unique line spectrum. You can think of a line spectrum that an element produces as its signature. It's going to be the same every time, and it's different for every element. Okay, starting in 3, 2, starting in 3, 2. And the colors on the line spectrum represent different forms of energy. You may know this already, but different types of light or electromagnetic radiation contain a different amount of energy. And remember as well that there are forms of light or electromagnetic energy that are outside the visible spectrum. So, for example, UV light is something that we as humans cannot see, and it's just outside the visible spectrum. And it's higher in energy than green light, say. And green light is higher in energy than red light. Then we have very low forms of energy, like radio waves, and those are even lower. They're outside the visible spectrum as well. So here's an example of the line spectrum for 3 different elements. And in this line spectrum here, we're only showing the lines that are in the visible spectrum. So these are the wavelength of the light, and This is just the range that's in the visible spectrum. So as you can see right here, each different element, hydrogen, lithium, sodium, each of them produce different lines on the line spectrum. So these were all known facts, and what Bohr did was explain the line spectrum in terms of atomic structure. So we offered an explanation, and that involved a new model of the atom. So let's now connect the line spectrum to his model of the atom. So when the line spectrum is a result of heating an element, so what happens when you heat an element, you're putting energy in, and in that case, the electron can absorb some of that energy. And if the electron absorbs enough energy, that electron can be excited to a higher energy level. So let's just take a look at that here, and we see that on the right. So say we have the hydrogen atom with one electron on the first energy level. Energy is put in, that electron absorbs some energy, and if it gets enough energy, it can jump to a higher energy level. In this case here, we'll just say it jumps to the second energy level. But that excited state, where that electron is up on the second energy level, is only temporary. Eventually, that electron falls back down to its ground state. When the electron loses that energy has to go somewhere, and it is released as light. So Bohr said that we see that release of energy as a distinct line on the line spectrum. Each line represents a certain amount of energy. And so what Bohr said was that the line represents the difference in energy between the higher energy state and the lower energy state. So you could say that when we see the line on the line spectrum, that represents an electron falling back down to its ground state.